Metals, nonmetals, and metalloids are our biggest groupings here on the periodic table, but there are other ways we can classify the elements. So we can classify them a little differently based on electron configuration. So we could group the elements here, we could group them into one of four groups. We could say the representative elements. These would be elements in groups 1A to 7A. So basically it would be the S's and the first five P's on your periodic table. We could classify them as representative elements. They might be metals, they might be nonmetals, but the key is it's just a different way of grouping them, and we call them the representative elements. So if you're looking on the table here, it would be these S's here and the first five P's, but not the last column of the P's. So any element here, obviously those are metals, but we could classify them as representative elements as well. And same thing over here. These over here could be classified as metals or nonmetals, but they can also be classified as representative elements. And then in the middle here, in the D block, we have what's called the transition metals. And then we have down here in the F's, another way of grouping this, we have the inner transition metals. So they're also known as the rare earth metals. And then finally, the very, very far right column of the periodic table is called the noble gases. All right, so we already know that when the P block is fully filled, those are called your noble gases. So this is just a different way of grouping the elements based on electron configurations. So you have representative elements in the S's and the first five P's, transition metals in the D block, inner transition metals or rare earths in the F's, and then you have the noble gases in the far right, the very last column there of the table. So now what we're going to do is we're just going to start working our way through some of these different columns in these groups. So we'll start with the representative elements first and work our way through some of the columns, and then we'll talk about all the groups here. The first column we're going to talk about in the representative elements is going to be the alkali metals. So this would be the far left column of your periodic table, just not hydrogen. So what I would do right now is I would have my periodic table out and I would label that column alkali metals. So it goes from lithium on down to francium, but not hydrogen. So this first column here is known as the alkali metals. And you can see it up here in green. So I would point at those elements on my table and label them alkali metals. So what we're doing now is we're just going through the representative elements here. These are obviously metals, but we're talking specifically about the column here. And this is a group that's in the representative elements, if you remember how we just grouped it. So these guys are in group 1A or group 1, if you're numbering left to right, 1 to 18. They are very reactive. Their electron configurations would all end in S1. So like lithium would be 2s1, sodium would be 3s1, potassium would be 4s1, and so on. And they all lose one electron and form a 1 plus charge when they form ions. We'll talk about why this happens later in the video, but for now, you need to know that these form a 1 plus charge. They lose one electron. All right, so now that you could talk about these in terms of, these elements in this column are all metals, but now you know something more specifically. They are alkali metals, and you have some more specific properties here. So we'll move through these groups a little bit faster now, but you definitely want to label these groups as we go through them. And these guys, lithium down to francium, are known as the alkali metal. Just a little extra information here. We said that the alkali metals are very reactive. They're actually extremely reactive in water. Some of them actually catch fire. So from lithium down through francium, those are your alkali metals, and they're pretty violently reactive in water here. They usually catch fire. They might, spark or pop, depending on, if the hydrogen gas given off catches fire or not. So there are some fake videos on YouTube showing like cesium in water and blowing up. It's not like that. They just do react pretty quickly with water, and they can sometimes catch fire and give off sparks and stuff like that. But they're not going to like blow up like you would think. Some of these videos, like I said on YouTube, are fake, but they're very reactive in water. We are going to move over now to the right one column. We're still in the representative elements. We're still in the metals here, but this column is going to be called the alkaline earth metals. So from beryllium on down to radium. All right, that column 2 there, group 2A or group 2 are the alkaline earth metals. I would point at this column and label them alkaline earth metals. They are going to be somewhat reactive. And notice my choice of words there. They're not going to be violently reactive, but they're going to react pretty much instantly. It's just that they're not going to, catch fire or anything like that. Pretty much, if you had one of these elements like calcium and you expose it to the air, it pretty much reacts instantly and starts to form, calcium oxide. It starts to oxidize or like rust. It's just not going to do it violently, but they are very reactive. They all are going to end in S2s for their electron configuration. And the alkaline earth metals like to lose 2 electrons and form a 2+ charge when they form ions. And again, we'll talk more specifically about this, why this happens later on in the video. But for right now, just know that they form a 2+. So label the column beryllium on down to radium. They are the alkaline earth metals, not alkali earth metals, alkaline earth metals. The next group of representative elements we're going to talk about are the halogens. If you notice, I skipped a couple of these representative element columns. The boron group, carbon group, nitrogen group, oxygen group. Basically, they are generic groups. They don't get a special name. Like notice we were talking about the alkali metals or the alkaline earth metals, and now the halogens here. So these 4 groups here, they just get generic names. The boron group, the carbon group, the nitrogen group, and the oxygen group. The element that's at the top, that's what you call the entire column. They're not special enough to get a name. So you just have to realize that whatever element's at the top of these guys, we call them by that name, and we name the whole group, the boron group. So now we're at the halogens here, fluorine on down. Sometimes astatine here is not classified as a halogen. We usually just talk about fluorine, chlorine, bromine, and iodine here. But I would definitely label them. They're group 7A or group 17. So they're just one from the left here of the very end of the periodic table. They are very reactive as well. Seems like the groups that are very reactive are the ones we talk about. They all end in P5 for their electron configuration, and they like to gain 1 electron and form a 1- charge when they form ions. Again, we'll talk about why in a little bit. So definitely label this column on your periodic table as halogens. We're going to talk about them as we go through the course, and you need to know that that group is the halogen. Now that we finished up some of the columns here and the representative elements, we're going to move to these bigger groups. So we have here in the D block, the transition metals. All right, so that's your D block here. Be careful up here on this picture. We call this F group down here the inner transition metals. So that's not what we're talking about when we talk about transition metals. It's just the D block. So anytime we see the D block here, those are transition metals. They grow from groups 3 to 12. They're all the D sublevel. Their charges can vary, so we don't know if they're going to be 1+, 2+, or even sometimes multiple charges, but we know they're going to be positive because they're metals, and metals all form cations or a positive charge. So we don't know the exact charge, but we know they're going to be positive, and the D block here is going to be the transition metals. So definitely label them on your periodic table. The F sublevel here, we're going to label the inner transition metals. So we already know the bottom 2 groups. We want to label inner transition metals. Probably a good idea to label them rare earth metals as well. But another thing you want to label here, so I don't know if you want to pause and get some of these labels in, but each of the rows also gets a special name. So the top F or the 4F here, we call that the lanthanide series. You can see up here, the 4F is going to be the lanthanide series because it starts with the element lanthanum. So they call the entire row the lanthanide series. And then the bottom F here, we call that the actinide series. So the 5F, we call the actinide series. That's the very, very bottom of the inner transition metal. So they have a few names here, and you definitely want to be aware of all of them. So together, the entire F here is called the inner transition metals or the rare earth metals. The top F is called the lanthanide series. The very bottom row is called the actinide series. All right, so definitely pay attention to their names and label them on your table. And then finally, the last group we want to talk about here are the noble gases. This would be from helium on down. It's the far right column on the periodic table. definitely label this group on your table. So it's going to be group 8A or group 18 if you're numbering 1 to 18 left to right. They all end in P6s, so they all have a completely filled P here. This makes them not very reactive, and they're actually really stable. So all of these noble gases have their outer energy level completely filled. All right, so typically they're going to have that maximum number of valence electrons. They want that 8 valence electrons. All the S and P for the highest energy level are going to be filled here for those noble gases. So they're very stable. They're happy. They have the number of valence electrons that they want. They're completely full, and they don't have any charge. They're just very stable, very happy. So the very far right column of your periodic table, make sure it's labeled noble gases, and definitely know they're extremely stable and they're not very reactive at all. As we were going through these different groups, we said, hey, some of these columns, some of these groups have similar properties. So why are these families, why are these groups so similar? It all comes down to the fact that they all have the same number of valence electrons. If you remember, the valence electrons are the outermost electrons here for an atom. And remember, the entire column has the exact same number of valence electrons. So if the valence electrons are the ones that are involved in the reactions, they're the ones that are involved in determining the properties here of the elements. All right, it makes sense that if an entire column has the exact same number of valence electrons, that every element in that column, you would expect them to act in a similar fashion. And the key here is all elements want that magic number of 8 valence electrons, because that means their outer energy level, their highest S and Ps, are full. All right, so the valence electrons here are very important. The columns, the families, they are similar because they all share the same number of valence electrons. We're going to talk a little bit more here about ions before we end this video. So we already know that ions are just charged atoms, atoms that have a plus or a minus with them. So any atom that is neutral, all right, has no charge, so the protons and the electrons are equal. Anytime that an atom has the protons equaling electrons, they just are neutral and they have no charge. But we know that atoms can lose or gain electrons here, making them ions. You can never change the number of protons, but the electrons can change to give them a charge. If the protons and the electrons don't match up, that's what makes ions here, and the atoms then have a plus or minus charge. Cations are ions that are positively charged. So there's a couple ways to remember this. If you love cats, this is going to be very easy for you to remember. People who love cats always just remember, hey, cats are a positive thing. So that's something that the way they remember it is just, cations are positive here. So you have to figure out a way that works for you, but you need to know that cations are ions that are positively charged. So if an atom is positively charged, that means it has lost electrons. Remember, electrons are negatively charged particles. So if you lose negatives, you are now more positive. So cations lose electrons. You need to know that the metals are going to be the ones that are forming cations. Metals always form the positives in terms of their charge. So you need to know this. This is something that's very important as we go forward in chemistry. The metals are going to be your positives. And how many you lose determines your charge. So if you lose 2 electrons, you're going to be a 2 plus. If you lose 3, you're going to be a 3 plus, and so on. So a good example here is magnesium. Magnesium likes to form a 2 plus charge. So when magnesium forms an ion, it loses 2 electrons and forms a 2 plus charge. So you definitely need to know cations, positively charged, they're losing electrons, and this is going to be your metals. Here's just another example. You can see sodium. Sodium has 11 protons and typically 11 electrons when it has no charge, but sodium will lose 1 electron, giving it 10 electrons, but it will still have 11 protons because it has to have 11 protons in order to be sodium. So it forms a 1 plus charge here. So anytime you lose an electron, that's going to be a positive charge, a cation. Anions here are just going to be the opposite. The anions are going to be negatively charged ions. Anions sound a lot like onions to me, which I don't like. So this is easy for me to remember that anions are negative. Also, the second letter there is N. So you can remember that's going to be negative, stand for negative. However you want to remember this, you just need to know the difference between anions and cations, and anions are negatively charged. So anions are gaining electrons. Electrons are negatively charged. So if you gain negatives, all right, if you gain electrons, you're going to be negatively charged, you're going to be an anion. And these are your nonmetals. You need to know that the nonmetals are forming a negative charge. The nonmetals will gain electrons. And what number charge is going to be based on how many electrons you gain. If you gain 3 electrons, you're going to be a 3 minus charge. So chlorine here is a good example. Chlorine likes to form a 1 minus charge. All right. And whenever the number is 1 plus or 1 minus, you don't have to write the 1. You could just write Cl minus in this case, and it means the same thing. It's totally up to you. You can put the 1. You don't have to. When it's not, 1 plus or 1 minus, if it's 2 plus, 2 minus, so on, you have to put the number with it. But chlorine likes to gain 1 electron and form a 1 minus charge. So your anions, negatively charged, gaining electrons, these are your nonmetals. Here's that example of chlorine. Chlorine typically has 17 protons, 17 electrons when it's in its neutral, no charge state, but chlorine likes to gain 1 electron, and you can see here in the nucleus, still has 17 protons in order to be chlorine, but now has 18 electrons, so it has 1 more negative. So it's chlorine 1 minus or chlorine minus. Anions, negatively charged, all right? These are going to be your non-metals that do this. If you're struggling here to understand this losing and gaining, think of it like dieting. If you're trying to lose weight, losing electrons, losing weight would be a positive thing. You're losing negatively charged electrons here, so you're positive. If you were gaining weight and you're trying to lose weight, that would be a negative. Just like if you're gaining negatively charged electrons, your charge would be negative. So just be careful here. Make sure you understand this and you know the difference between anions, cations. What actually determines the charge here? What determines if an element wants to be a 1 plus or a 2 plus or a 3 minus? Well, it's going to be the location on the periodic table. Location, 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 and the number of valence electrons. So it makes sense here if we're talking about the valence electrons being important. Each column has the same number of valence electrons. Each column is going to have a specific charge that it likes to form. So right now, I would get out your periodic table and label these charges on your table. You need to be able to look at your periodic table and know these charges without it being labeled. So you need to have them there so you can reference it for now. All right. But the very far left column here on the table, your alkali metals, this entire column is going to be a 1 plus charge. So the entire column here, from hydrogen on down, every element in that column is going to form a 1 plus charge when they form an ion. And you need to know this just by looking at the periodic table. So if we move over to the right here, the alkaline earth metals, these guys always form a 2 plus charge. So the entire column. We will skip the transition metals here. We know that they're metals, and we know that they're going to be positive, okay? But we don't need to know the exact number positive that they're going to be. Then we're going to come over here to the boron group. They like to form a 3 plus charge. So the entire column, boron on down, 3 plus charge. We're going to skip the carbon group here. All right, we don't need to worry about the charge for that group or column. So we're going to move over to the nitrogen group. They're going to be a 3 minus. Oxygen group is going to be a 2 minus. The halogens are going to be 1 minus. And then we know that the noble gases have no charge. So make sure you've labeled your periodic table. This charge that we wrote at the top applies for the entire column. You need to be able to look at your table and know, like phosphorus, okay, that's going to form a 3 minus charge, whether it's labeled there or not. This is very important when we do naming next unit and beyond. You need to be able to look at your table and know what the charges are for a particular column. So make sure it's there and make sure you know this. Remember here, these atoms are looking to have that magic number of 8 electrons in their outer or highest energy level. They want 8 outer or valence electrons in order to be stable. So basically, all these atoms want to be like a noble gas. So to form their charge, they're basically gaining or losing electrons in order to be like a noble gas in terms of their electron configuration. Realize here that when atoms gain or lose electrons, they're not becoming a noble gas because their protons are not changing. But in terms of their electron configuration, they are gaining or losing electrons so that their electron configuration resembles a noble gas. And they do what's ever easier. So think about this. If you have something like magnesium here, an element like magnesium, magnesium wants to have 8 outer electrons. Magnesium wants to be like a noble gas. So magnesium here could lose 2 electrons and be like neon, or think about it, if magnesium has 12 electrons, lose 2, magnesium would look like neon in terms of his outer or his electron configuration here for his valence electrons, or magnesium could gain 6 and be like argon. Okay, remember, we're not gaining protons, we're just talking about gaining electrons here so that the electron configuration resembles a noble gas, because that's what they want to be like in terms of their electron configuration. Well, you can lose 2 or gain 6. They do what's easier. Magnesium is going to lose 2 electrons so that his electron configuration resembles neon, and he can be happy or stable. So all elements want to do this. They want to either lose or gain to be like a noble gas in terms of their electron configuration. I want you to practice this real quick. Just determine if each of these would form a cation or anion, and then give the charge that they would form. So use your table, pause the video, and do this right now. Cation or anion and the charge that forms. So pause the video. Hopefully, these are the answers you got here. All right. Any of the elements that are positive, those are going to be your cations, because remember, cations are positive. So calcium and francium are both going to be cations, and then your negatives, bromine and phosphorus, are going to be your anions, because anions are negative. And then remember, you just look up these charges based on where they're at on the periodic table. So for example, calcium is in the 2 plus column, so he forms a 2 plus charge. And remember, for these 1 plus, 1 minus, you could just write the charge as minus or plus. You don't have to write the number with it, but you do have to write the number for anything above 1. So you should be able to look at your table, determine if any element is a cation or anion, and you should be able to know the charge now.